The second ensemble method we're going to cover is boosting method. So what is the boosting method? The main difference between boosting and bagging is the following. The first one is in boosting, unlike a bagging method, each data has its own weight value. And the weight value of each data represents the probability of being selected by a sample. Okay, that's the first difference. And the second difference is in boosting, each classifier has its own weight value. Okay, and the weight value of each classifier means the importance of each classifier. Okay. So there are two weight values in boosting, weight values of each training data and the weight value of each classifier. Okay, so these are our two main modifications, differences between boosting and bagging. And this one shows the abstract level structure of boosting. So in the boosting, as I said here, each data has its own weight value. And in the beginning, each data has the same weight values, okay? And then we do sampling, and using the sample, we construct a new classifier. And in boosting, we call it weak learner, okay? So we build a new classifier or a weak learner using the sample. And then now the weight value of each data is recomputed, okay, based on the result of classification. Okay, we're gonna talk about this a little bit later, but we build classifier, okay, and for each data we make predictions, and depending on the result of prediction, we recompute the weight of each data. Okay, so that's the basic structure of boosting, and we keep doing this, okay, repeatedly. And when training is done, finally the final classification is based on the weighted voting of weak learners. So as I said here, each classifier has its own weight. Okay, so because of this, we do the weighted voting of these weak learners, and the result of this voting becomes the final classification value. Let's talk about the strong learners and the weak learners. Strong learner is a classifier with very high accuracy. So let's say we have classifier whose accuracy is like 99.9 something, then we call it a strong learner. And actually, it is very difficult to build a strong learner. Yeah, think about it. You build an algorithm whose accuracy is over 99%. Okay, it's extremely difficult to do. Okay, so maybe the example of a strong learner can be SVM or deep learning. Okay, so anyway, a strong learner is very difficult to construct. Okay, and the other one is weak learner. Weak learner is a classifier whose accuracy is better than random guessing. Okay, so you have a classifier and whose performance is better than random, then it is weak learner. Okay, so actually this is very easy. This constructing weak learner is very easy, right? As long as its accuracy is over 0.5, it is weak learner. So it's a very easy job actually, right? So the example of a weak learner can be a decision stump. This is the most simple decision tree form. Okay, So this may be, even though this is very simple classification model, it is still weak learners. So we have learned many classification algorithms, and if you choose any one of them, okay, then most likely that algorithm is weak learner because its performance is better than 0.5. So that is weak learner. So in ensemble learning, the question now we have is, can we somehow collect a set of weak learners? Okay, we collect a set of weak learners and make them into a single strong learners. So is it possible? That is the question of ensemble learning. And the answer is yes. We use the boosting method. So by doing so, we combine many weak learners, okay, and then we turn them into one single strong learner. Okay, that's the basic idea of a boosting method. So I said in boosting, each data has weight, and this weight is updated after classification is done, right? So here we're going to explain how these weight values are updated. But before I do that, I'm going to give you an analogy of boosting using other example. Suppose you took a test. Okay, there are many questions in the test, and then you got some of them right. Okay, and you got some of them wrong, right? And then next time you restudy the material, those questions again, probably you focus on the questions you got wrong, right? So by doing this repeatedly, okay, and then probably you're gonna get all the questions right, okay, in the end, right? So this is actually the basic intuition behind the boosting method, okay? So if you make some error, okay, in the data, then next time you focus on this error, okay? So by doing this repeatedly, probably you're gonna solve entire data, okay? So that's the intuition behind this boosting method. So again, each data in boosting has weight value. In the beginning, each data has the same weight. Okay, you start with uniform weighting. And then if that data is misclassified, okay, it's not correctly classified, then you increase the weight of data, okay. On the other hand, if that data is correctly classified, then you decrease the weight of data, okay. So remember, the weight means the weight value of data represent the probability of being selected by the sample, right? So increasing weight value here means next time in the next sample, probably this example will be selected, okay, in the next round, right? Decreasing this weight means this example is less likely to be selected in the next sample, right? So it makes sense, okay? If this data is not correctly classified, okay, then you're gonna focus on this example, okay, by increasing the weight, okay? And suppose this example is correctly classified, then you know the answer, right? This problem is solved. Then by decreasing the weight, and this data is less likely to be selected next round, okay? So that makes sense. So that's how we update the weight values of data. So again, as I said, the intuition is we focus on difficult problems which are not correctly classified in the previous steps. Okay, so by doing so, hopefully we can solve in all the problems correctly. Okay. Let's take a look at the example here. Let's say we have 10 original data. Okay, and then again, each in the beginning, each data has same weight. And in round one, using boosting, we do a sampling, and this is the first sample, okay? And using this sample, you build a classifier or whatever it is, okay? You can build any weak learner. It doesn't have to be strong learner, okay? So it can be anything. You can be decision tree or neural net or SPM, whatever, okay? And using that classifier, you make a prediction here, okay? And then suppose, okay, suppose this data 4 is misclassified, okay, is not correctly classified, okay. Then next time in next round, actually you increase the weight of this data 4. Okay, so if a certain data is misclassified, you increase the weight value of this data. So suppose this data 4 is misclassified, then you increase the weight of data 4. Okay, so because of that, in next round, you see more of data 4. We see 3 of them. Okay, in previous round, you have 1, 4, and next round we have 3 over 4, right? And suppose okay, still this data 4 is still this is not correctly classified, then we increase the weight of data 4 even more. Okay, so next round you have more of data 4. This time we have 5 of 4. Okay, so as you can see here, if a certain data is misclassified, you increase the weight of the data. So that way, in next round, you want to see more of the data. Okay, so in this case, suppose 4 is misclassified, then the next round we see more of data 4, and let's assume still this data 4 is misclassified, then we increase this weight even more. So next round we have more of data 4. Okay, so that's how we update the weight values of data. So as I said here, as the record that are misclassified will have their weights increased, and on the other hand, if records are correctly classified, then it's going to have their weight decreased. Okay, so that's how we update weight of data. In boosting, we have seen that each data has its own weight, but actually in boosting, each classifier has its own weight as well. So in boosting, unlike the bagging where majority voting is used, in boosting we use weighted voting because each classifier has its own weight. So we after training is done, we combine the prediction of each classifiers by using weighted voting. So we construct a strong classifier by weighted voting of the weak classifier. So when you combine the prediction of weak classifiers, we use weighted voting. So a better weak classifier gets a larger weight. So the weight value of each classifier actually means the importance of each classifier. So if a certain weak classifier has high accuracy, then it has a high value of weight. Okay. So in boosting, we keep adding we keep adding samples, right? So in each sample, we create a weak classifier. Okay, so we iteratively add new weak classifiers in boosting, and each classifier again has its own weight. This one shows an example of using a boosting method. And suppose we have 4 data, and the length of each data represent the weight of data. And we also have classifier, and the size of this classifier is the weight of classifier. Okay, so in the beginning, each data has the same weight. Okay, and using this sample, we construct a decision tree like this. We assume we use a decision tree as the weak learner. And then using this classifier decision tree, we classify this data. And suppose these two are correct and these two are wrong. Okay. Then for these two, because these are misclassified, we increase the weight of these two. So in next round, the weight of these two becomes bigger. And also for these two, these are correctly classified. That means the weight of these two are smaller now. So these we have smaller weight for these two. Okay. And then again, we are using this. We construct another decision tree classifier like this, okay? And we classify this data using this classifier now, okay? And let's say these three are correct answer, and for this is error, okay? By the way, if you look at the size of each classifier, for this classifier, so I said the size of classifier is the weight of a classifier, and the weight of classifier means the importance of a classifier. So for this case, its accuracy is actually half, right? 2 of them is right, 2 of them is wrong. So the accuracy of this classifier is 50%. For this one, you got 3 right out of 4. So the accuracy of this classifier is 75. So this is better than this one. Okay, that's why this decision tree is bigger, okay, than this one here in this picture. So anyway, now these 3 are correct and this is wrong, right? Then you increase the weight of this one, which becomes like this. And for these 3, you reduce the size, the weight value. So it becomes smaller like this, okay? So using this one, you construct another decision tree and you classify using this decision tree, and you have these 2 are correct, these 2 are wrong, and the accuracy is half, okay? So its accuracy is half is not good, it's as good as this one. So the size of this is same as this one, okay? So because these 2 are wrong, we increase the weight of this and this, which is here and here, okay? For these 2, these are correct. That means we reduce the error of these 2, okay, which is this and this. So finally, using this, you build another decision tree, and suppose now this decision tree correctly classifies entire data, okay? So everything is perfect now. So because accuracy of this classifier is 100%, the size of this classifier is the largest among these, okay? So this picture shows the weight values of data and the weight values of classifiers. This one shows the pseudocode of boosting method. Let's say the M is the number of weak learners we're going to generate. So in the beginning, we set the same weight values for all the examples. For example, every weight value is 1 or something. Then for I equals, I varies from 1 to m, m is number of weak learners. We generate the classifier h sub I, okay, and then using this hi, we classify examples, okay. So from the predictions of this classifier hi, we decompute the weights of each data. Okay, if the prediction is correct, we decrease the weight. If the prediction is wrong, we increase the weight. And then we also recompute the weight of each classifier. Okay, the weight of classifier is again the importance of classifier, and the weight goes up. If the accuracy of classifier is high, the weight of classifier is high as well. Okay. So anyway, for every class, for I equals 1 to m, we repeat this. Okay. So when this is done, finally we do a weighted voting, okay, using all these m classifiers. Because each classifier has weight values, we are able to do a weight voting, okay, using all these classifiers. So that is the final answer of this ensemble boosting method. Actually, there are many variations, okay, depending how to set the weight values here, how to recompute the weight values, or how to combine these classifiers here, okay. So depending on the way we compute these weight values of data or weight values of classifier, there are many variations of boosting method. And in the next slide, we're gonna learn one of the most famous boosting method, which is called the AdaBoost, in the next slide. There are many variations of boosting method, depending on the way we update the weight values of data and the weight values of classifiers as well. So among them, one of the most famous one is AdaBoost algorithm. So we're going to explain this AdaBoost algorithm here. This algorithm, AdaBoost, was proposed by Yoav Freund and Robert Shapiro in 1996. So suppose we have T different classifiers. And in this slide, we're going to show how to compute the importance of classifier or the weight value of classifiers. Okay, so in this case, it is denoted as alpha I. So alpha I is the importance or weight of classifier I. Okay, so this slide actually shows how to compute the weight value of classifier alpha. Okay. So let's say we have classifiers, and let's say EI is the error of classifier I. Then the definition of EI is given as this. So if you look carefully here, for every data, okay, j equals 1 to n, n is number of data. So for every data here, for every data j actually, then Cixj is a prediction from classifier I, right? So this is prediction from classifier I, and this is the correct value of data j. So if this is not equal, then this is error, right? And this delta is identity function. So if this delta p is true, if this is true, delta returns 1, okay? Otherwise returns 0. So this is true means this is error, right? Yj is the true value, true target value of data j, and this is the prediction by classifier I about xj, right? So this is not equal. That means the prediction from classifier I is wrong, right? So this means this is error. And this is multiplied by the W here is the weight value of data J. So this one is multiplied by the weight value of data J. Okay, and we do summation of this for every data. So that is the definition of the error of classifier I. Okay, this is definition of classifier I error, size of error. So simply put, the error of classifier I actually is the summation of weight values of misclassified data. Okay, so error of classifier is basically the summation of weight values of misclassified data. Okay, so that's definition of the error of classifier I. This one is just a normalization constant. Okay, so it's not very important. Okay, so this is the final definition of error of classifier I. And then the weight value or importance of classifier is defined as follows. So alpha I, the weight or importance of classifier I is 1/2 times log 1 minus error I over error I. Okay, this is definition of the importance or weight value of classifier. Okay, so this picture shows the shape of this function, this one. Okay, so x-axis is error, and this y-axis is the definition of the importance of classifier alpha. So as error increases like this, the value of alpha, okay, importance of weight value decreases monotonically. Okay, so that makes sense. Okay, if a certain classifier has high error value, then its importance becomes smaller, right? It makes sense. So on the other hand, if a classifier has very small error, then it has very high importance value, right? So this shows the shape of this function, and actually it makes sense. And this is the importance or weight value of classifier being used in AdaBoost algorithm. So in previous slide, we have seen how to update the weight values of classifiers in AdaBoost. Here, we're going to see how to update the weight values of data in AdaBoost. So the formula goes like this, okay, and Wi is the weight value of data I. So this is new weight values, and this is current weight value, okay. So new weight value of data I is equals to the current weight value times either this or this, okay? So if this is prediction made by classifier J, okay? So if prediction is equal to the target value, this means there is no error. This is correct answer, right? So if the answer is correct, then this one is multiplied by this, okay? On the other hand, if this prediction, okay, is not equal to the target value, this is error, right? So if error happens, this one is multiplied by this, okay? So about this alpha j, so in previous slide, so alpha j was what? It was the importance or weight of classifier j, right? So alpha j is the weight or importance of classifier j. And this one is actually always positive. Okay, the reason is if you look at the shape of this function alpha, then if the error, okay, if the error of classifier J is less than 0.5, okay, then this alpha value is always positive. If you look at the shape of function of alpha function, okay, shape of this alpha value. So and in AdaBoost, by the way, if a certain classifier, for a certain classifier, if its error is over 0.5, that means a certain classifier, its performance accuracy is worse than random caching, right? Its error is over 0.5 means the classifier is worse than random guessing, right? So if that happens in AdaBoost, we simply threw that away, okay? We just kill the classifier and create the brand new classifier, okay? So we can always assume the error is always less than 0.5, because if error is over 0.5, we just kill it, okay? So because error is always less than 0.5, the alpha j, the weight of classifier, is always positive, okay? So this alpha is always positive. So back to here, if there is no error, okay, then the current weight value is multiplied by this, okay? And because alpha is always positive, this whole thing is less than 1. If you remember the shape of exponential function, if alpha is positive, then minus alpha is negative, right? That makes this exponential less than 1, right? So so that means actually if there is no error, okay, prediction is correct, then the current value is multiplied by a number which is less than 1, okay? If prediction is incorrect, error, then current weight value is multiplied by a number which is greater than 1, okay? So that means if there is no error, this is multiplied by a number or value which is less than 1. That means in this case we decrease this value, and if there is error like this, then this is current value is multiplied by this one which is greater than 1. That means in this case we actually increase the value of this, right? So that's how it works. If there is no error, we decrease the current value. If there is error, we actually increase this value. Okay, so that's the way we update weight values of data in AdaBoost. Finally, this Zj is a normalization factor, and that is just nothing but the summation of entire W values. By the way, as I said here, if in AdaBoost algorithm, if a certain classifier, if the accuracy is less than 50%, we simply remove, okay, throw that away and create a new classifier, okay. And finally, when the training is done, we simply do the weighted voting of entire classifiers, okay. Okay, now let's see how AdaBoost algorithm works using an example. Suppose we have 10 original data. It has X value and Y is the class label, is binary 1 or -1 like this. And so again in AdaBoost, in the beginning, each data had the same weight values, okay? So in round one, each data here has the same probability of being selected. So as a result, in round one, let's say we have this sample like this, okay? And again, as we did in bagging example, let's use decision stump as our weak learner, okay? So this is the best decision stump you can find in this particular sample. So this is decision stump, and it says if x value is over this, the class label is 1. If x value is less than this, then class value y is -1. Okay, that's decision stump for this sample. So if you apply this decision stump to original data, okay, you draw a line here, and everything here is 1, everything here is -1. Okay, then we have error here. You draw a line here in the original, and decision stump says everything. If x is over this, y value is 1, and if x is less than this, y is -1, right? So we have 3 error here, okay? So if you come down here, these are the weight values of each record. So in the beginning, for each data, their weight values are same, 0.1, okay? So each data has same weight. So after round one, we have this decision tree, and from this original data, then if you apply this decision stump to this original data, we have 3 error here, right? So as a result, the weight of these 3 has increased. So we have seen here, the weight value of these 3 has increased from 0.1 to 0.31, okay? For the others, actually, their weight has decreased because for this data, they are correctly classified, okay? That means their weight values will be reduced, okay? So that's the result here. And in round 2, okay, using these weight value is a probability to be selected. So using these weight values, we do another sampling. Okay, that's the result in round 2. As you can see here, there are many 0.1, 0.2, 0.3. The reason is the value of these 3 is very high probability of being selected, okay? So if we compare this, the weight of these 3 is 0.1, 0.31, and the weight values of these are 0.01, okay? So this is significantly larger than this one, so that's why we have a lot of 0.1, 0.2, 0.3, okay? So from this sample, we find a decision stump like this, okay? So that means if for every x value, y value is 1, right? So you apply this to original data like here, then this decision stump says every y value is 1, right? So every y value is 1 here, and we have error here, okay? These are error by using this decision stump, right? So these 4 are errors. So we have to increase the weight value of these 4, okay? Because of this decision stump, it is error for this 4 data, right? So for this 4, the weight value has increased from 0.01 to 0.23, like this, okay? And on the other hand, for the others like these are not errors, so we reduce the error of these like this, okay? So from 0.31, it now becomes 0.03, okay? So that's how it works. And as you can see here, the weight values of record changes. If it is correctly classified, it reduces like this. If it is incorrectly classified, it increases like this, okay? So we have three round of samples, and for each sample we have a classifier. In this case, we have a decision stump. And as you remember, in AdaBoost, each classifier also has its own weight values. So in this picture here, in each round of sample, we have a classifier, and these are the alpha value, which is the weight or importance of this classifier. So this one here, for the first classifier, its weight is 1.738. For the second classifier, the weight is 2.778, and the third one, its weight is 4.119, right? Again, this alpha value can be computed using the error of classifier. Okay. So anyway, now every classifier has a weight, and let's do a weighted voting here. So we have 10 original data, and we have 3 classifier, and each classifier has these weight values. So we do weighted voting. The prediction of first classifier was -1. Okay, the prediction of second and third classifier was 1, 1. Okay, so we do summation of weight value, class weight values for the class of -1, and we add the class value, we add the classifier attribute for the class value of 1 here. Okay, so for this one, its class weight value is this one, 1.738. And for this one, it should multiply by 2.778. And for this one, it's multiplied by 4.119. Okay. So this minus this is 5.16. Okay. We do the same thing here. Let's say we have like this here, x equals 0.4. And the prediction of first classifier is -1. Prediction of second classifier is 1. Prediction of third one is -1. Okay, so again, for this one, should multiplied by this one. This is multiplied by this one, and this one is multiplied by this one. Okay. So for the class of -1, we add this and this. That means add this and this. And for the class of 1, we simply use this one. Okay, so we do plus minus math here, and the final summation is minus 3.08, right? So for every data, we do this summation. Okay, so final summation is 5.16, 5.16, etc. So this is positive. That means the final answer is 1. This is positive 1, 1. This is negative -1, -1, -1, -1, 1, 1, 1, right? And the last row here is the true class value, which is given in original data, right? So these are the true class label, and this is the final prediction from this AdaBoost algorithm. Okay, so as you can see, we have a perfect match between true class label and the final prediction of AdaBoost algorithms. So that's again the beauty of AdaBoost algorithm. And as we know, the accuracy of each classifier is not very high. Okay, as I said many times, in AdaBoost or other boosting algorithm, each classifier is called the weak learner. Okay, that means their accuracy is not very high. So that's why we call it weak learner. But when you combine them, when you combine many weak learners, we can see here, okay, all together it becomes very strong, okay, very powerful, very competitive algorithms. Okay. So that was AdaBoost algorithm. And here we're gonna see some pros and cons of AdaBoost algorithm. And even though this AdaBoost algorithm is quite simple and easy to implement, it is still widely used in many applications, and this algorithm is quite competitive actually. Okay, so advantage of AdaBoost is this is very simple to implement. You simply collect any weak learners. Okay, you can. There are many weak learners you can choose from. Okay, you collect some of them and run the AdaBoost. Okay, so it's very simple, easy. And it's even though the algorithm is simple, it shows pretty good performance. Okay, its accuracy is pretty high, and as I said, this is quite competitive algorithm compared to other state-of-the-art method. And this advantage is the answer we get from AdaBoost is not is not global optimal. Okay, so there is no guarantee that the answer we get from AdaBoost is global optimum. Okay, so we have suboptimal problem. The main problem of AdaBoost is this one. This algorithm is sensitive to error or noise data. Okay, the reason is if you remember the mechanism of AdaBoost, each data has weight. Okay, if data is a certain data is misclassified, we increase the weight. Okay, and that actually increase the probability of being selected, right? But think about this: if that particular data is error, then this AdaBoost algorithm focuses on error. Okay, this algorithm is trying to solve an error problem. Okay, so that is a problem. Okay, so its algorithm is somewhat sensitive to noise data. Okay, so because of this, if your data has a significant amount of noise or error, it is not recommended to use AdaBoost algorithm in your case, okay? Because this AdaBoost algorithm is sensitive to noise data, okay? Final note here is sometimes you may wonder, okay, so in AdaBoost, yeah, including many other ensemble method, it consists of many weak learners. Okay, so weak learner is the algorithm its accuracy is just over random guessing, right? So you may wonder, what if we use very state-of-the-art algorithm like a decision tree as the base classifier in AdaBoost? Okay, you can do it, but actually, if you use very sophisticated, very complex algorithm as the base classifier in AdaBoost or many other ensemble method, in many cases, actually it degrade the performance of AdaBoost. Okay, the algorithm converges too fast because base classifier the base classifier is too good. Okay, it actually accelerate the convergence of algorithms, so it learns too fast. Okay, so actually this AdaBoost with the decision tree has been quite good. It's referred to as the best of the shelf classifier. So AdaBoost with decision tree actually may be better than AdaBoost with let's say a deep learning. Okay, so that's very a little one very interesting property of AdaBoost. Okay, so if weak learners are actually quite strong, okay, like if you use a very state-of-the-art deep learning or something, okay, it actually doesn't help. Okay, so if the your classifier is too complex, the test error may be larger than the training error. Okay, it may be it actually degrade the performance of your AdaBoost algorithm.